Okay, so the recording has started. Okay, so the book has a nice introduction in the start there of section 8.2 series. I'm going to use an example to help introduce the series. The reason is you just learned what sequences are, and now I think a series. I want to show you the difference between the sequence and the series. Hence, that's why I'm doing this example. So take a moment to copy it down. Okay, so we have this sequence, and we want to know if the sequence converges. Let's do part A. Let's talk about part A first. So this sequence here, does it seem like this sequence would converge? And if so, what do you think the sequence converges to? That's right, Marvelous. 4/3. I mean, so the way you want to think about it is intuitively, and I'm not saying show work like this, but in your mind, you're letting n go to infinity. So think of 4 times infinity. I mean, this is sort of like, thinking. Now, this isn't how I want you to show your work, but if you had 4 times infinity over 3, and I'm putting this in quotes because it's just sort of like what's going on in your mind. 4 times infinity over 3 times infinity plus 1. Is this little 1 here, does that little 1 really change the value much? Does it really change the value when n is large? Does that 1 really? That's right, Marvelous. That's right, Tyreek. Not really. So it's like 3 times infinity over, or 4 times infinity over 3 times infinity. If you sort of like, I'm not going to cross that out, But in my mind, I'm ignoring the 1. I want to get this in blue. I'm ignoring the 1. And so I get 4/3. Okay, if I ignore the 1, 4 times infinity over, I got to be a little careful, but the ends here are the same infinities, you know. So 4/3, it makes sense. So the sequence converges, and we can certainly list out terms and to get a feel for the sequence. We could graph the sequence on our TI-8384 calculator, and you would see that the sequence is 4/3. I tend to like, algebraically, you just, if you let n goes to infinity, I can multiply the top and the bottom by 1/n and rewrite this sequence in a more pleasant form, because here it's very easy to see that, hey, 1/n, as n gets large, that goes to 0, and you're left with 4/3. I mean, this is going to equal 4/3 plus 0. How many of you feel that it's helpful putting in this step here to rewrite the sequence in this form here? Thank you, John. Thank you, Robin. Excellent. Thank you, Josiah. Excellent. Josiah's here. Thank you, Francesca. Thank you, Ryan. Excellent. And it isn't hard to do. It's not hard to do. A lot of times in math, if you're doing something and it seems really hard, you may not be doing the problem right. But anyway, 4/3 is the answer. So the sequence converges to 4/3. Are there any questions on that? Okay, all right. Now we get to part B. Determine whether the series converges. So the series, this is the series. What does this symbol here mean? That Greek symbol, sigma. What does that stand for? You've seen that before in pre-calculus. That's right, Samaya. Very good. Summation. It's a summation. So what you're doing with the series is you're adding up the terms of the sequence. You're adding up the terms of the sequence. So if we go to the solution here, this is what you're doing. This is what summation means. So you're adding up the terms of this of the series. Remember, the first term of the series was 1. I mean, let me just go back for a minute. We'll come back to this, but if you look here at the terms of the series, and remember the series was 4n over 3n plus 1, right? So the first term of the sequence, now I'm talking the sequence, is 1, because 4 times 1, 4 times 1 over 3 times 1 plus 1 is 1. The second term of the sequence is 8/7, because 4 times 2 is 8, And then in the denominator, 3 times 2 plus 1 is 7, 8 sevenths. The third term of the sequence is 12 tenths. That's when n equals 3. 4 times 3 is 12, and then 3 times 3 plus 1 is 10. Are we okay with these terms of the sequence? Are you intuitively comfortable? I mean, I hope you are, but maybe give me a thumbs up if you're. Thank you, John. So I'd like to hear more. I'd like to see more thumbs up. Good. All right. Good. Thank you. Thank you. Excellent. All right. Anybody else here? Is everybody comfortable with that? All right. So the series says take the terms of this sequence and add them. So I'm going to take 1 plus 8 sevenths plus 12 tenths plus 16 thirteenths and so forth. I'm adding the terms of the sequence. Thank you, Ryan. And what I want to know is, I want to know if this sum, I'm going to be adding, I'm going to add terms. I'm going to add terms, an infinite number of terms I'm going to add. I want to know if this sum is going to approach a number. Is it going to approach a number? Is the sum going to converge? That's what I want to know. What do you think? Do you think this series is going to converge, or do you think it's going to diverge? That's right, Josiah. It's going to diverge. The series is going to diverge. Let me ask you this. In order for the series to converge, what would have to happen to the terms of the series, as you keep going out to infinity? What eventually happens to the terms of the series? What do they have to do? In order for that series to converge, what might eventually the terms of the series have to approach in order for the series? That's excellent, Robin. 0. Now that's a necessary condition. The terms of the series need to approach 0 in order for the series to have a chance to converge. But it's not a sufficient condition. You can have a series, like for example, harmonic series, and we'll talk about that probably tomorrow. We'll get into the harmonic series. But you can have a series where the terms of the series actually approach 0, but the series diverges. That can actually happen. And the reason is that the terms of the series need to approach 0 quick at a sufficient rate so that the series converges. It's just like with improper integrals. When you had like a limit of an integral, well, you have an integral where one of the endpoints is infinity. The area gets smaller, and the tail area might get smaller, but the area is accumulating, but it has to accumulate at a rate slow enough so that the improper integral converges. It's the same kind of thing with series. So this series diverges, and the reason the series diverges is because the terms of these series are going to approach 4/3. If you go out, many terms, the terms of the series are going to start looking very much like plus for like 4/3, plus 4/3, plus 4/3. I mean, remember that the terms of the series approach 4/3 because the sequence approaches 4/3. So if you add up a bunch of 4/3 together, you're going to get infinity. So this series diverges because the limit of the term of the sequence is 4/3, and that's not equal to 0. And this is what's called test for divergence. This is called the test for divergence. If the terms of the series are not approaching 0, the series will diverge. That's by test for divergence. All right, are there any, so I'm trying to present Section 8 in an intuitive way for you so that you're, comfortable with the concepts. Are there any questions at all? Okay, all right. Well, let's go in the book for a moment. I want to go in the book here. Let me just go in the ebook. And I want to look at a series that actually converges. So let me see here. I'm going to have to log back in, so give me just one moment. Okay, so I'm logging back in to WebAssign. Going to student view. Okay, so I'm going into the ebook. Okay, so let me stop sharing here and go into share the application. Chrome, MindTap. Okay, so I'm in the ebook here, and you're welcome to follow along here in your ebook, Infinite Sequences and Series. Okay, there's some nice videos here embedded in the ebook. That's good. All right, so I'm going into section 8.2 series. And I'm going down, I mean, here's 8.2, and I'm going down a little bit. There's some interesting stuff here, but I want to look at this this series here. So this series, you have the series where n equals 1 to infinity of 1 over 2 to the nth power. So you're adding up an infinite number of terms. Okay, what's the first term of the series? 1/2, because when n equals 1, 1 over 2 to the first power is 1/2. What's the second term of the series? 1/4. 1 over 2 to the second power is 1/4. Okay, when n is 3, you're going to have 1 over 2 to 1 over 2 to the third power. That's 1/8. The fourth term is a 16th, and so forth. So this infinite series, you're seeing some of the terms of the series, and it turns out that this series converges. If you add up these terms of the series and you're adding an infinite number of terms, you're going to get 1. You're going to get 1. Now, why is this? Why is this? Well, the way you can intuitively understand this is by looking at what's called the sequence of partial sums. The sequence of partial sums. Okay. So, like when n equals 1, the first partial sum is half. That means you just have the first term of the series. The second partial term, the second partial sum, so the first partial sum is a half. The second partial sum is 0.75. How are they getting 0.75 for the second partial sum? Where's that coming from? How did they get that? So when n is 2, the second part, that's right, John, 0.5 plus 0.25, very good. The second partial sum, 0.75, is the sum of the first two terms. What about the third partial sum, 0.875? How are they getting the third partial sum? What are they adding there? That's right, Robin. The first term, second term, and the third term. 0.5 plus 0.25 plus an eighth is 0.125. That's 0.87. And so what they're doing is they're studying these partial sums. And they're letting n increase. And what seems to be happening to the partial sums of, what seems to be happening? If we look at this sequence of partial sums, if we look at the sequence of partial sums here, what does the sequence seem to be approaching? That's right, Marvelous. Very good, and Robin, very good. 1. So you see, because the sequence of partial sums approaches 1, we can say that the series, the infinite series, converges to 1. So the formal definition of if we go to the next page here, let me see. I don't want to go. Hold on. Somehow I got all the way to the x. Oh wait, I got to go down. That's okay. I got to go down. Definition. So if you have the nth partial, so given a series, let S sub n denote its nth partial sum. Its nth partial sum. If the sequence of these partial sums converges, and the limit of the sequence equals S, okay, then the series is convergent, and the sum of the terms of the series equals S. In other words, the infinite series equals S. The number is called the sum of the series. If the sequence diverges, then the series is called divergent. Okay. So this is formally how you can formally use this definition to show whether a series converges or diverges. Okay, that's the formal definition. But of course, it takes a lot of effort to make a table of partial sums and then study the partial sums as n goes to infinity. Okay, as n gets large, to see if there's convergence of the series. So for some special series, we can come up with ways to determine whether the series converges or diverges. And I'm going to just continue in the ebook here. Okay. One special series is called a geometric series. Okay. Geometric series is a very special series. But tell you what, let me get to the example here. Let me get to the example here. Yeah, let me get to the example, and then what they're doing there will make a little more sense for you. So okay, this here in this second example, this series is called a geometric series. Take a moment to copy it down. Okay, so I mean, looking at this series, I mean, we're calling this series a geometric series. Okay, we're calling it a geometric series. Is there anything sort of interesting about this series? I mean, you see some kind of interesting pattern looking at the terms. First term of the series is 1, and then the second term of the series is a third. Third term of the series is a ninth. Fourth term of the series is 1/27th. What do you think, by the way, the next term of the series would be? What do you think the next term of the series would be here? That's right, Tyreek, 1/81. That's right, Josiah. Okay. And what about the next term of the series? That's right, Marvelous. That's right, Francesca. Excellent. 1/243. That's right, Ryan. Thank you. So I mean, are there any questions on that? The fact that we're able to state what and of course the series goes on, right? But the fact that we're able to list the next two terms of the series tells us that we understand this series. And incidentally, what are the terms of the series seem to be? I mean, are the terms of the series getting larger, or are they getting smaller as we go out in the series? They're getting smaller. That's right. Thank you. Thank you. And what do they seem to be approaching? The terms of the series. That's right. Thank you. Thank you. So many good responses here. 0. So this series has, I mean, and I'm saying find the sum of this geometric series. So in order for there to be a sum, that means the series has to converge. Well, the terms of this series are approaching 0, Now again, that's not enough to say the series would converge, but since this is a geometric series, the series does converge. And it seems that, you know, 1 times a third is a third. A third times a third is a ninth, right? A third times a ninth is a 27th. Okay. And so a third is relevant here, right? For this geometric series, a third's relevant. Now, another way to think about it is if you take 1/3 and divide it by 1, you get a third. If you take the second term and divide it by the first term, you get a third. A third divided by 1 is 1/3. If you take the third term, which is a ninth, and divide it by the second term, a third, you're going to get what? What is a ninth divided by a third? That's right, Josiah, a third. Oh, we got a third back again. Okay. What if we take the fourth term, 1/27th, and divide it by the previous term, 1/9? 1/27th divided by 1/9 is a third. So see, this is what we call a common ratio. Every geometric series has a common ratio. And you can find the common ratio. I mean, every term, if you take that term of the series and divide it by the previous term, you're going to get a third. That's a common ratio. Okay, so if we look at the solution here, again, we want to find what the sum of the series is, but this here just demonstrates what I mentioned here, that you know, like the second term a sub 2 divided by the first term a sub 1, that's the third. The third term a sub 3 divided by the second term a sub 2, that a sub 2, that's a third. This is a geometric series with a common ratio of 1/3. The question is now, what is the series going to equal? Okay, well, so again, we have 1 plus a third plus a ninth plus a 27th. The first term, by the way, we call that A. With the geometric series, the first term is A equal to A. Now, what I want to do is I want to write a formula for this series. I want to write a formula for this series. In other words, you know, I'm going to have a summation where n equals 1 to infinity, but I have to figure out what goes, you know, what the pattern is. Well, it turns out that you can write this series I mean, we've enumerated 4 terms of the series. The series keeps going. But if we want a formula, this geometric series is going to be the series, the sum, where n equals 1, where n equals 1. Sorry. This infinite series, the formula is going to be the sum, where n starts at 1, goes to infinity, of 1 times 1/3 to the n minus first power. The common ratio, R, is a third. So anytime you have a geometric series, you can express that geometric series as a summation where n goes from 1 to infinity of a to the r to the n minus first power. Okay, so you have to identify you have to identify what A is. A is always the first term of the series. You have to identify what the common ratio R is. Well, you know how to do that. And then you have an n minus 1 to the first power. Okay, so that's these geometric series have patterns to them. Now, it turns out that the common ratio, a third, that's less than 1. And if we take the absolute value of the common ratio, and that absolute value is less than 1, the series will converge. And in fact, okay, so if it converges, what's the sum? Well, the sum is going to be equal to the formula A divided by 1 minus R. A divided by 1 minus R. Well, A was 1, that was the first term of the series, and then R is a third, so 1 minus a third in the bottom. Again, the formula is A over 1 minus R. And that's actually proven in the book. That's proven in the textbook. In example 1, they actually prove that formula. Right now, I just want to focus on some examples, but perhaps feel free to look at the proof. So this is your answer then, 3/2. 3/2. So the series, the series equals 3/2. Okay, are there any questions on that particular example? All right. Well, let's take a look. Let's take a look then at a second example. I'll move on. Everybody's okay with the notes here? Okay. Let's move on. Another example. We want to find. Hold on here. I want to be a little bit careful here. Yeah. I want to find the sum of this geometric series. Okay, so take a moment to copy it down. All right, so what would the common ratio be? So this geometric series is an alternating geometric series. The first term is positive, second term is negative, third term is positive. It's alternating geometric series. Can anybody tell me, for this alternating geometric series, Can anybody maybe offer what the common ratio is? Excellent. Robin and Marvelous are correct. Negative 2/3. I mean, so one way to think about it is 5 times negative 2/3 is negative 10/3. But that means negative 10/3 divided by 5 is negative 2/3. Okay, negative 10/3 times negative 2/3 is 20/9. If you go from the second term to the third term, negative 10/3 times negative 2/3 is 20/9. Well, 20/9 divided by negative 2/3 is negative 10/3. So the common ratio is negative 2/3. Now the absolute value of negative 2/3, the absolute value of negative 2/3 is less than 1. So this is going to be a convergent geometric series, and the terms of these series are getting smaller. Now, it's going to take a while for the terms of the series to get close to 0, but they are decreasing. So let's look at the solution. Then, are there any questions on that? Let's look at the solution in the book. So the solution, I actually quote it from the book. Okay. And here's the little box, by the way, that gives the information regarding a geometric series. Let me just try that again. And we wanted to find the sum of the geometric series. So since the formula is for a convergent geometric series would be the sum would equal A over 1 minus R. Well, the first term of the series is 5, right? So that's your A. And then you have 1 minus the common ratio of negative 2/3. So that'll be 5 over 5/3, and that gets you 3. And that would be what the sum is. And again, what do we really mean when we say that this sum is 3? Again, what you can do is you can look at the partial sums of the series. So the first partial sum is 5 because that's the first term. Second partial sum is 1.66667. How are they getting this second partial sum? Based on our series, how are they getting this second partial sum? Who can chat it out? How are they getting that? Well, the second partial sum, when n is 2, we're at this here equals, right, s sub 2. It's the sum of the first 2 terms. So how do we get that sum of the first 2 terms? What are they adding together? What 2 numbers? Who thinks they can tell me? That's right, Marvelous. Excellent. They're taking 5 minus 10/3. 5 is 15/3. 15 thirds minus 10 thirds is 5 thirds. That's 1.6 repeating. The third partial sum, S sub 3, they would be taking, to get that, they'd be taking 5 minus 10 thirds plus 29ths. Okay, and if you do that on your calculator, you'll see 5 minus 10 thirds plus 29ths is 3.8 repeating. Okay, and then they keep finding the partial sums here. And as you let n increase, so like S sub 10 would be the sum of the first 10 terms of the series. This is the 10th partial sum. What do these partial sums appear to be approaching? What do the partial sums appear to be approaching based on the table? That's right, Josiah. Excellent. 3. And what they've done here is they've made a little graph where they've graphed, you know, they have 20 partial sums. And of course, you have the first 10 partial sums here. And they just plotted those partial sums and looked at the sequence of partial sums. Okay, so the first partial sum, right, was 5. So there's 5. Second partial sum was 1.6 repeating. There it is. Third partial sum is 3.8 repeating. There it is. And they're just studying the partial sums, the sequence of partial sums, as n gets large. And it's approaching 3. So, you know, it's important to remember how the idea of what it means for a series to converge. For a series to converge, the sequence of partial sums of the series have to approach a number, and they approach 3. However, and that's good. I mean, that's important. We're going to need to make use of that fact for some upcoming problems. Hello, Dr. Carbone. Good to see you. So, but keep in mind that for a convergent geometric series, we have a formula that can give us the sum of the series. Now, if you didn't want to use that formula, you could, for every geometric series problem, you could construct a table, and you know, based on the table, you do enough partial sums, you'll get an idea of what the sum is. Okay. How many, though, prefer using the formula? Give me a thumbs up if you prefer using the formula. Okay. Robin, John, Tyreek, Michael. Okay, Michael. Good to hear from Michael here. All right. So, yeah, I like everybody to, you know, participate. Fortunately, we have a formula here. Now remember, if the absolute value of the common ratio is greater than 1, then the series diverges. Okay, the terms are getting bigger, right? So they're growing out of control. Okay, well, let's look at another example here. Let's look at another example. Now in this example, I'm saying, if possible, find the sum of this series. If possible. So, you know, I'm not saying it's possible, but if it's possible, if the series converges, find the sum of the series. So, okay, go ahead and copy this example down. All right. So for this series, notice that the starting value is n equals 0. It's okay to do that. Traditionally, you're used to seeing series where the starting value instead of n equals 0 is n equals 1. Okay? But in fact, series don't have to start at n equals 1. They can start at n equals 0. They can start with n equals 2. They can start with n equals 100. What matters in terms of whether the series converges or not is how the series behaves as n gets large. Okay. So does this series resemble any series? I mean, that might be interesting. I mean, we could write this series could we write this series that way? Is it okay to write this series this way? So I have 1 to the nth power in the numerator. Is that okay? That's absolutely right. That's right, Josiah. 1 to the nth power equals 1 always. So what I'm getting at here is this series then can be written then like this. Right? You can, this series here is the same as this series. I just rewrote the series. Now, why would I want to rewrite the series in this interesting way here? Why would I want to do that? I mean, what kind of series could this possibly be? That's right, Robin. Very good. This is a geometric series. It's a geometric series. Let's see. You know, I mean, well, let's look at a few more details. So let's go to the solution here. And what I have here, I'm trying to get this fairly big. Can't have it that big. So we agree that we can write the series where n equals 0 to infinity of 1 divided by the square root of root 2 to the nth power as the series where n equals 0 to infinity of 1 over square root of 2 to the nth power. We can do that. And if you were to write out some terms of the series, you'd have, you know, the first term would be 1 over square root of 2 to the 0th power. Second, plus 1 over square root of 2 to the first power, plus 1 over square root of 2 to the second power, and so forth. These are the terms of the series. So what's the common ratio? What's the common ratio? I mean, if we were to I mean, it's going to get a little crowded here, but if I were to take these terms here, okay, and have 1 over square root of, no, scratch that. If I were to take the terms of this series here, I'd have 1 plus, because 1 over root 2 to the 0, 1 over square root of 2 to the 0th power is 1. I'd have 1 plus 1 over square root of 2. 1 over square root of 2 quantity squared is 1/2. The next term would be 1 over 2 square root of 2. But the point is, do you see, how many find this helpful helpful here, this enumeration, and seeing that we have a geometric series? How many find listing of the terms to be helpful? Good, thank you, John. Thank you, Tyreek. Absolutely, and so the common ratio is 1 over root 2. Thank you, Ryan. That's right. Thank you, Daryl. Appreciate all these responses, and that's why when I can, I try to, hey, mention your names, right? You'll be a little bit famous, right, in the recording. So, okay. This is a geometric series, and what I want to do is I want to write the geometric series in the. I want to have the series, instead of starting at n equals 0, I want to start it at n equals 1. Now this is just one way to find this sum, okay? I'm doing it one way. The formula in the book, says if you have a convergent geometric series, the sum where n equals 1 to infinity of a times r to the n minus 1, that'll equal a over 1 minus r. Okay. So I'm sort of, right? So, so what I'm doing is, well, the first term of the series is 1, right? Is 1. So that's A. Common ratio is 1 over root 2, and then n minus 1. So, but the thing is, you see, I guess what I'm trying to say is, like, okay, let me circle this part. Okay, I don't want you to. I mean, there's a sum here, right? There's a sum here. Where n equals 1 to infinity, right? Okay, so the thing is, what complicates things a little bit in this problem is n starts at 0. If you want to use this formula here, then we want n to start at 1. Well, in the blue here, I've written out the first 3 terms of the series for n equals 0, n equals 1, n equals 2. Okay? If I want, instead, the first term of the series to start be this term where n equals 1, the second term of the series be the term for n equals 2, third term of the series be the term for n equals 3, I need to adjust my exponent as n minus 1. You see? because zero, no, I'll do that here. 0 is 1 minus 1. So n is 1. 1 minus 1, 0. 1 here is the same as 2 minus 1. So, you know, n is 2. 2 minus 1 is 1. And the 2 here is the same as 3 minus 1. So if I change the starting value of my series, of my sum, to n equals 1, if I change n equals 0, if I bump it up to start the series at n equals 1, then the exponent, the nth power, has to be taken down 1, reduced by 1, and so you have n minus 1 to the first power. Does that make sense? Does that, okay? Are there any questions on that? Manipulating the series is useful, right? Okay, so that means then that the series then, by the formula here, by this formula, the series is going to be equal to a over 1 minus 1 over root 2. That's 1 over 1 minus 1 over root 2. So that's going to be, then you can simplify that to root 2 over root 2 minus 1. And that's your sum. That's your sum. The series does converge. But you know what you can do, there are several ways to do the problem, okay? One way is to, let me make that a little bit lower, a little bit less. One way is to try to take your series that you start with and rewrite it. Let's get that in maybe purple. Rewrite the series. And thank you, Dr. Carbone. Just a reminder, WebAssign help session tonight, 8 to 9, with Dr. Carbone, if you're interested. Two ways to sort of get this sum. One way is to take the series and rewrite the series in a nice form, okay? Once you get it in the nice form, you can just apply the formula and get the sum. Another way, though, is to take the terms of the series, enumerate some terms of the series, and you know the first term is 1. You know the common ratio is 1 over root 2. So just do 1 over 1 minus 1 over root 2. Okay, so sometimes there are advantages to one approach compared to the other approach, but I'm trying to show you different ways. Are there any questions on that? Any questions? Okay, let me stop recording here.